All right, let's get right into it. You've probably heard this a million times, right? An AI model has billions of parameters, and that number is getting closer and closer to the number of neurons we have in our brains. It's a super exciting comparison that makes you think, wow, are we about to create a digital mind? But, and this is a big but, it brings up a huge question. Are we even measuring these two things on the same scale? And hey, this isn't some high-level academic debate either. This is the exact kind of question that pops up on places like Reddit. Real people are wondering about this stuff. So when you put an artificial neuron next to a biological one, is it really a fair comparison? Is it, an apples-to-apples thing? Or is it more like comparing a paper airplane to an F-22 fighter jet? Let's dig in and find out. So to really get a grip on where we are today, we kind of have to rewind the clock and go back to the very beginning. See, the whole idea of artificial neural networks didn't just magically appear. It was born from a very specific, very ambitious goal: to figure out how to describe the brain using math, and then try to copy it. And if you look at this early timeline, you can see those biological roots crystal clear. It starts way back in 1943. You've got a neurophysiologist and a logician, an unlikely pair, right? They team up to create the very first mathematical model of a neuron. Their whole goal was just to understand how the brain creates these incredibly complex patterns. Then, fast forward to 1958, a psychologist, Frank Rosenblatt, comes along and builds on that idea with something called the perceptron. This was huge because it proved these little math-based neurons could actually learn from data. So you see, the brain wasn't just some vague inspiration, it was literally the blueprint. But then, everything changed. There was this huge shift, a real fork in the road for AI research. The entire community kind of stopped asking, how can we build a perfect copy of the brain? And they started asking a totally different and maybe more practical question. How can we build a machine that just gets the job done? Maybe even better than a person can. And the thing that really kicked off this change was an algorithm called backpropagation. Now, here's the simple way to think about it. Imagine the network takes a guess at something. Backpropagation is the process that looks at the answer and says, nope, you were this wrong. Then it sends that error message all the way back through the network, telling every single connection, hey, you need to tweak yourself a little bit so we do better next time. It's an unbelievably powerful way to just get better and better at a task. In this paper right here, this is it. This is the moment. The 1986 paper that really brought backpropagation into the spotlight. It was a total game changer. Almost overnight, neural networks went from being these kind of theoretical toys for neuroscientists to becoming brutally effective machines for solving really hard problems. So here's the key takeaway from that moment. With backpropagation now in the driver's seat, the goal wasn't to build something that looked and acted like a real brain anymore. Nope, the new goal was pure raw performance. As one research paper put it so well, the field just rapidly diverged from trying to copy how the brain actually works. Okay, so they diverged. But the question is, just how different are they now? Well, this is where things get really interesting. We're about to get into the nitty-gritty, and you're going to see why that simple one-to-one comparison between an AI neuron and a brain neuron just completely falls apart. Get ready for this number. 5 to 8. What does that even mean? Well, according to one analysis, you need an artificial neural network that is 5 to 8 layers deep just to start simulating the complexity of a single biological neuron. Let that sink in for a second. One of our brain cells, just one, has the same computational power as a small, multi-layered deep learning model. That's insane. And this chart really lays it all out. On one side, you've got the artificial neuron. It's clean, it's predictable, it's just a math function. But a biological neuron? Oh man, that's a whole different beast. It's complex, it's messy, it's governed by physics and chemistry. The AI learns with that neat backpropagation algorithm we talked about. But how our brains actually learn? We still don't fully know. Artificial networks are usually structured to flow in one direction, nice and orderly. The brain, it's a chaotic, tangled web of connections going every which way, with feedback loops all over the place. The differences are just staggering. Oh, and we haven't even talked about the power bill yet. This is another huge one. Your brain, the incredibly powerful machine in your head right now, is a masterpiece of efficiency. It runs on about the same amount of power as a dim light bulb. Seriously. Now compare that to training a big AI model. That is a massively energy-hungry process with a very real impact on the environment. And just to put that into perspective, take a look at these numbers.
Training just one of these big AI models can pump out over 600,000 pounds of CO2. That's more than 5 times the emissions of a car over its entire lifetime, including all the gas it burns. It's just a completely different league. Our brains do what they do using a tiny, tiny fraction of that energy.
But hold on. After all that, you might think AI and neuroscience have nothing to do with each other anymore. But that's not the whole story. Even after that big split, the brain is still a huge source of inspiration for AI. And in some of today's most powerful AI, you can still clearly see the echoes of that original biological blueprint. And the absolute best example of this is in computer vision. You've heard of convolutional neural networks, or CNNs. These are the engines behind things you use every day, like facial recognition on your phone, or the systems in self-driving cars. And the amazing thing is, their whole design is a direct nod to how our own brains make sense of the visual world. I mean, look at this. The parallel is just stunning. On the left, you see how our visual cortex works. It has simple cells that spot things like edges, and complex cells that piece them together into patterns. And on the right, a CNN does pretty much the exact same thing, just with math, using what they call convolutional and pooling layers. It's just this beautiful moment where biology provided the inspiration for a brilliant engineering solution.
So, after all that, what's the big takeaway? Where does this leave us? Well, it means we really need to adjust how we think about all this. The brain is an amazing analogy for AI, a fantastic starting point, but it's not a perfect one. It's super important to remember that we aren't building digital copies of our brains. Let's circle all the way back to that Reddit thread that kicked this whole thing off. One user just nailed it. They said ANNs and BNNs are very, very different, and it would be unwise to view them as even remotely close to one another. And that just gets right to the heart of it, doesn't it? That simple comparison, counting AI parameters versus brain neurons, it's not just wrong, it's totally misleading.
So, if there's one thing to remember, it's this. Artificial neural networks are not like little baby brains that are just waiting to grow up. That's the wrong way to look at it. They are incredibly sophisticated mathematical tools. Yes, they were inspired by the brain, and yes, they still borrow ideas from its architecture, but they are not on some path to becoming a perfect copy of it. They're a completely different kind of intelligence. And that leaves us with a really fascinating question to chew on. If we stop thinking of AI as a competitor to our brain, and instead start seeing it as a powerful new tool for understanding our brain, what changes? What secrets about our own minds, about our own biological intelligence, will these amazing and very different artificial systems help us unlock next?